There is a thought so corrosive to ordinary life that most scientists who encounter it do one of two things. They engage with it briefly formally and then close the door on it as quickly as professional courtesy allows, or they refuse to engage with it at all and explain their refusal with a shrug and a comment about having better things to worry about. The thought is not a religious idea. It is not pseudoscience. It has been published in peer-reviewed journals, examined carefully by philosophers of the caliber of David Chalmers at New York University, and sketched out mathematically by physicists with careers solid enough to risk the association. And yet, you will struggle to find a working experimental physicist who wants to sit with it at dinner. The thought is this: the universe you're sitting in right now, with its 93 billion light years of observable space, its 2 trillion galaxies, its strange and mathematically precise laws, might be a computation, not a metaphor for a computation, not sort of like a computation in some loose poetic sense. A literal running process instantiated on some substrate we cannot currently conceive of, operated by an agency or set of agencies we cannot verify, and almost certainly cannot communicate with. The rock under your foot, the light coming through the window, the firing of neurons that is allowing you to read these words, all of it, possibly information being processed according to rules that were set from outside. I want to be scrupulously precise with you from the very beginning, because the popular versions of this idea have buried its genuine, disturbing quality under layers of science fiction framing and internet speculation. This is not a claim that we are inside a video game. It is not a confident assertion that reality is fake or that your experiences have no value. What it is a serious logical and physical argument built from real observations about quantum mechanics, black hole thermodynamics, information theory, and the mathematical structure of physical law that makes the question of whether the universe is computational not obviously answerable in the negative. And when serious people apply rigorous reasoning to a question like that and cannot rule it out, the correct response is not to mock or to dismiss. The correct response is to sit very still and think carefully. That is what we are going to do together over the next hour and a half. I'm not going to tell you that you are definitely inside a simulation. I am not going to tell you that your life lacks meaning because it might be computational, or that physics has discovered something that makes existence feel hollow. What I will walk you through carefully and honestly is the question itself: where it came from, what the physics actually says, which versions of the idea have real evidence behind them, and which are wishful extrapolation, what the strongest objections are, and what it would mean for consciousness and experience and the nature of reality if the answer turned out someday to be yes. The question is uncomfortable not because the answer is obviously terrifying, but because the answer is genuinely unknown. And the structure of physics gives us some reasons, not proof, but reasons, to think the boundary between universe and computation may be thinner than common sense has always assumed. The universe you learned about in school was made of stuff. Particles of matter and energy moving through the 3 dimensions of space and 1 dimension of time, governed by laws that were discovered one by one over the past 4 centuries. Each law a new step in the conquest of mystery by reason. Isaac Newton found that the same equations governing a falling apple governed the orbit of the moon, a single mathematical law describing motion across all scales. James Clerk Maxwell showed that electricity, magnetism, and light were 3 faces of the same underlying phenomenon, unified by 4 equations of extraordinary elegance. Albert Einstein revealed that space and time were not fixed containers for events, but were themselves flexible, warped by the presence of mass, and that mass and energy were different expressions of the same thing. Then, in the first decades of the 20th century, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, Wolfgang Pauli, and their colleagues pried apart the atom and found something that none of Newton's intuitions had prepared anyone for. Matter at its smallest scales does not behave like stuff, it behaves like information. This is not a metaphor. This is the technical content of quantum mechanics. And it took the greatest physicists of a generation a decade of sustained work to understand even the outline of what it implied. An electron, before it is measured, does not have a definite position. It exists as a probability distribution, a quantum wave function, a mathematical object that describes not where the electron is, but what the probability would be of finding it at each possible location if you chose to look. The electron is not secretly hiding somewhere specific. While we remain ignorant of its hiding place, experiments by John Bell in 1964, confirmed by Alain Aspect at the University of Paris-Sud in 1982, refined by Anton Zeilinger and his group through the 1990s and 2000s, and verified again in loophole-free experiments by Bas Henson, Ronald Hansen, and colleagues at the Delft University of Technology in 2015, showed definitively that the electron's position before measurement is not merely unknown, but genuinely undetermined. The measurement does not reveal a pre-existing fact, it participates in creating one. The universe at its most fundamental level is not deterministic in the classical sense. It is probabilistic in a way that goes all the way down. This is not philosophy. This is what the equations say and what a century of experiments confirms. A particle in superposition spread across two or more states simultaneously collapses to a single definite state when interacted with in a certain way. Why? Nobody fully knows. The measurement problem, as physicists call it, remains one of the deepest unsolved problems in all of physics. Multiple interpretations of quantum mechanics exist. The Copenhagen interpretation, the many worlds interpretation developed by Hugh Everett III in 1957, the de Broglie-Bohm pilot wave theory, cubism, relational quantum mechanics, and others. And they all make identical predictions for every experiment we can currently design. The question of which one describes reality is by current evidence undecidable, but the empirical fact underlying all of them is not in dispute. At the most fundamental level, reality as we currently understand it is not made of tiny billiard balls. It is made of mathematical objects that describe probabilities, and those probabilities resolve into definite outcomes through processes that are themselves not fully understood. The conventional story treated this as a strange but manageable feature of small-scale physics. Yes, electrons are weird. Yes, quantum mechanics is counterintuitive, but at the scale of people, planets, and galaxies, classical physics works fine. Quantum weirdness in the standard teaching is quarantined from everyday life by the process of decoherence, in which quantum systems rapidly interact with their environments and lose their superposition character in a way that makes them look classical. Keep your head down, do the calculations, don't ask what it means. That was the implicit advice of physics departments for much of the 20th century. Richard Feynman said it more bluntly, shut up and calculate. But there is a crack in this story. Actually, there are several cracks, and they run in directions that are increasingly hard to look away from. The first crack appeared when physicists started thinking seriously about black holes and realized that the universe stores information in a way that is radically different from what common sense predicts. The second crack appeared when they started asking not what physics describes, but what it is a description of. Matter or patterns of matter, particles or the information encoded in particles. And the third and perhaps deepest crack appeared when John Archibald Wheeler, one of the most respected theoretical physicists of the 20th century, the man who coined the term black hole and who collaborated with both Einstein and Bohr, started asking whether information might not be a consequence of the physical world but its very source. Wheeler coined a phrase in 1989 that has haunted physics ever since. It from bit, not bit from it, not information as a product of physical processes, it from bit, the physical world as a product of or identical with information. He was not certain this was right. He spent the last decades of his life asking the question, not answering it. But he was enough of a physicist to recognize that the mathematics of quantum mechanics was pointing somewhere strange, and that somewhere was not quite the same place as the world of solid stuff that Newton's universe had promised. The universe at its deepest accessible level seems to be made of questions that nature answers when asked, silence in every direction and questions posed. To understand why serious scientists take the computational universe hypothesis seriously, we first need to understand what happened when physicists in the early 1970s started thinking hard about black holes. A black hole, in the simplest terms, is a region of space where gravity is so intense that nothing, not light, not any known signal, can escape. When something falls into a black hole, it is, from the perspective of external observers, gone. And for most of physics history, gone was understood to mean exactly that. The information about the object's properties, its composition, its quantum state, its history was simply destroyed. The black hole swallowed it, and it ceased to exist. Jacob Bekenstein, a graduate student working under John Wheeler at Princeton in the early 1970s, started questioning this. Bekenstein noticed that the second law of thermodynamics, the law that says entropy, the measure of disorder and missing information in a system, never decreases overall, was being violated every time something complex fell into a black hole. The total entropy of the universe appeared to go down because you were taking an information-rich object and dropping it into a region from which all that information vanished. This bothered him enough to propose something radical. Black holes must themselves carry entropy, and the amount of entropy is proportional not to their volume, but to the area of their surface, their event horizon. The information content of a black hole is written on its surface, not in its interior. Stephen Hawking initially thought this was wrong because entropy implies temperature, and temperature implies thermal radiation, and a black hole, by definition, cannot radiate. Anything that approaches its surface is captured, not emitted. Then, in 1974, performing the calculation properly with quantum field theory applied at the event horizon rather than using pure classical general relativity, Hawking found to his own astonishment that black holes do radiate. There is a faint thermal glow now called Hawking radiation that emerges from the region just outside the event horizon due to quantum effects at the boundary between interior and exterior. Bekenstein had been right. The entropy formula stood, and it had a precise form. The entropy of a black hole equals 1/4 of the area of its event horizon, measured in units of the Planck length squared. 1/4 of the surface area in Planck area units. Let that settle for a moment. The Planck length is approximately 1.616 times 10 to the minus 35 meters. It is the scale at which quantum gravitational effects become important. The smallest length that current physics can describe without breaking down. A proton is to the Planck length roughly what the observable universe is to a proton, a ratio of unimaginable magnitude in both directions. And the entropy of a black hole, which encodes the total information content of everything that has ever fallen into it, is measured by how many Planck length squared tiles you could fit on its surface, not in its volume. The information content of a three-dimensional region of space, all the richness of everything that has ever entered it, is encoded on the two-dimensional boundary surrounding it. The implications of this are difficult to fully absorb. In ordinary physics, the information content of a region of space scales with its volume. The more cubic meters you have, the more information you can pack in. A larger region can contain more stuff, and more stuff means more information. This is just the basic combinatorics of three-dimensional space. But a black hole violates this expectation in a specific and precise way. Its information capacity scales with its surface area, not its volume. A black hole 1 billion times larger has a surface area 1 billion squared times larger, but a volume 1 billion cubed times larger. The information scales with area, while the naive expectation says it should scale with volume. Something about the structure of black holes is fundamentally two-dimensional in its information content. Gerard Hooft, the Dutch theoretical physicist who shared the 1999 Nobel Prize in Physics for his work on the mathematical structure of quantum field theories, took this observation and generalized it in a 1993 paper. He proposed what he called the holographic principle. The idea that the information content of any volume of space is fully described by the information encoded on the surface surrounding that volume. Not approximately described, not effectively described, fully and exactly described. Everything that is inside is written on the boundary. The interior is in a precise mathematical sense redundant. Leonard Susskind at Stanford University developed this idea further, arguing that what had been learned about black holes was not a special property of exotic objects, but a general principle about the structure of spacetime. The universe in Susskind's framework is a hologram in a technical sense. A lower dimensional surface encodes all the information needed to reconstruct the three-dimensional interior. This is the origin of the holographic principle as a broad claim about physics, and it has become over the past 3 decades one of the central organizing ideas of theoretical physics. In 1997, Juan Maldacena, an Argentine-American physicist then at Harvard University and now at the Institute for Advanced Study in Princeton, published a paper that gave this idea its most precise and powerful form. The paper, The Large N Limit of Superconformal Field Theories and Supergravity, is now among the most cited papers in the history of physics, with tens of thousands of citations. Maldacena showed that a specific theory of quantum gravity in a 5-dimensional curved spacetime called anti-de Sitter space is exactly mathematically equivalent to a quantum field theory without gravity living on the 4-dimensional boundary of that space. The two theories describe the same physics, the same physical reality, but one uses a 5-dimensional description with gravity and the other uses a 4-dimensional description without it. Every event in the 5-dimensional interior corresponds precisely to a pattern in the 4-dimensional boundary and vice versa. You can compute anything in one and get the answer in the other. Maldacena's ES-CFT correspondence, as it is called, meaning anti-de Sitter space conformal field theory, is not a speculation. It is not a conjecture awaiting experimental proof in the normal sense. The two theories are mathematically identical in the contexts where both can be computed, and they have been used to make predictions about physical systems that have been confirmed. The correspondence has been applied to calculate properties of the quark-gluon plasma produced in heavy ion collisions at the relativistic heavy ion collider at Brookhaven National Laboratory in New York, where collisions of gold nuclei at near light speed produce a soup of quarks and gluons that briefly recreates conditions from the first microseconds after the Big Bang. The plasma's behavior, specifically its extraordinarily low viscosity, is captured by holographic calculations in a way that no other approach achieves. In plain language, what ES-CFT says is this: spacetime and gravity, the fabric of the 3-dimensional universe as we experience it, can emerge from a quantum theory living on a surface 1 dimension lower with no gravity at all. The 3-dimensional world is not the ground floor of reality. It is a projection from something simpler, something that lives on a boundary. You can compute everything about the 3-dimensional interior by knowing everything about the 2-dimensional boundary. The interior is, in a mathematical sense, that has survived decades of scrutiny, derivative. This does not prove the simulation hypothesis. The ADS-CFT correspondence describes a mathematical equivalence between two descriptions of the same physics. The universe we live in is not exactly anti-de Sitter space because it is expanding, which makes it closer to de Sitter space with a positive cosmological constant. Whether the correspondence has an analog for our specific universe remains an active research question. But what ADS does establish with mathematical rigor is that the intuition that 3-dimensional space is fundamental, that the volume of a region is the right thing to count when you count information, is not a law of nature. It is a habit of thought, and habits of thought, when they conflict with mathematics, lose. In April 2003, a Swedish philosopher named Nick Bostrom, then a researcher at the University of Oxford's Future of Humanity Institute, published a 13-page paper in the Philosophical Quarterly titled, "Are You Living in a Computer Simulation?" It is one of the most discussed and contested papers in contemporary academic philosophy, and it deserves to be explained carefully because the popular paraphrase of it, that Bostrom proved we are probably in a simulation, misses the argument completely. Bostrom did not prove that we are in a simulation. He proved something both weaker and stranger: a trilemma, which is a structure that forces you to accept at least one of three uncomfortable conclusions. The trilemma runs as follows. Consider the future trajectory of civilization. Assume that at some point, technological civilizations become capable of running detailed, high-fidelity simulations of minds, whether those minds are digital reproductions of biological brains or entirely artificial conscious processes running on powerful computers. Bostrom calls this reaching post-human status, meaning a level of technological development substantially beyond our current capacities. Given that premise, at least one of the following must be true. Proposition 1, the fraction of civilizations that reach posthuman status before destroying themselves is very close to zero. Almost all technological civilizations go extinct, whether through nuclear war, engineered pandemics, ecological collapse, misaligned artificial intelligence, or some other catastrophe before they reach the stage of being able to run mind simulations. Proposition 2. The fraction of posthuman civilizations that choose to run large numbers of simulations of their own ancestors or of other minds is very close to zero. Almost all civilizations that reach that level of capability choose for some reason not to use it in this way. Perhaps ethical concerns about creating conscious beings without their consent. Perhaps a simple loss of interest in the past. Perhaps some discovery that makes the project seem pointless or harmful. Proposition 3. We are almost certainly living in a computer simulation right now. Why does the third proposition follow if the first two are false? The reasoning is probabilistic and requires one key assumption that the number of simulated minds, if any civilization runs simulations at scale, would vastly outnumber biological minds. Think about how many simulations a mature civilization might run. Each simulation could contain billions or trillions of conscious entities. Over the civilization's history, they might run thousands or millions of such simulations. The ratio of simulated minds to biological minds would quickly become astronomical. If you are a mind and you have no way of knowing whether you are biological or simulated, and the ratio of simulated to biological minds is something like a trillion to 1, then Bayesian reasoning says you are almost certainly simulated. Bostrom himself, in subsequent papers and interviews, was careful not to assert personal confidence that the third proposition is the true one. Based on his own statements, he assigned roughly equal probability to all three. Perhaps 1/3 to the extinction scenario, 1/3 to the choice not to simulate, and 1/3 to the simulation conclusion. A 1 in 3 probability of living in a simulation is considerably higher than intuition would suggest, but it is also considerably more honest than the popular summary, which tends to flatten the argument into a simple, "we're probably in a simulation" claim. The most intellectually consequential part of Bostrom's argument is not third proposition. It is the structure of the trap it sets. To escape the simulation conclusion, you must accept either that civilization is almost certainly doomed, or that advanced civilization consistently chooses not to explore its own past through simulation. Both alternatives are interesting in their own right. The first resonates with every serious analysis of existential risk, the fragility of complex technological societies in the face of their own power. If the vast majority of civilizations that reach our level of development fail to make it through the next few centuries, then the simulation question is the least of our problems. But it does lend a certain weight to the case for taking those risks seriously. The second alternative resonates with philosophy. What kind of civilization with essentially unlimited computing power consistently chooses not to use it to simulate? Perhaps one that has resolved the hard problem of consciousness and understands the ethical weight of creating experiencing beings. Perhaps one that has found meaning in something else. Perhaps one that has discovered a reason we cannot currently conceive of. In the 2 decades since Bostrom's paper appeared, numerous philosophers have examined and refined the trilemma. Nick Beckstead, Toby Ord, and other members of the broader existential risk research community at Oxford have connected it to the general question of what happens to civilizations as they acquire more power. The philosopher David Deutsch has challenged the statistical reasoning underlying the argument. The physicist and author Sabine Hossenfelder has argued that the argument imports assumptions about consciousness and substrate that it cannot justify. The philosopher Eric Schwitzgiebel has pointed out that the simulation hypothesis, even if true, changes nothing about the practice of science because the laws of physics we observe would still be the laws of physics we must reckon with, whether or not they are the real laws or the simulated ones. Each of these objections is worth taking seriously. None of them demolishes the trilemma's basic structure. What they collectively establish is a set of constraints. The argument is valid but rests on premises that can be questioned. And the probability you should assign to each branch depends heavily on assumptions about consciousness, about the future trajectory of civilization, and about the ethics of simulation that are themselves deeply uncertain. The purely philosophical argument would be provocative but containable. What makes it genuinely difficult to dismiss is that the physical structure of the universe has over the past century accumulated a set of features that are consistent with computation in ways that were not expected and that are not obviously explained by any other framework. Begin with quantization. One of the central features of quantum mechanics is that many physical quantities come in discrete steps, minimum units below which no smaller amount exists. Energy is quantized. Angular momentum is quantized. Electric charge is quantized. You cannot have half a photon or a charge of half the elementary charge or angular momentum below the minimum quantum. Reality at the most fundamental accessible level is granular. It comes in packets. This is not an approximation or a practical simplification. It is a feature of the universe that has been confirmed in countless experiments over a century. And it has no parallel in the physics that came before quantum mechanics, which treated energy, momentum, and charge as continuous quantities that could take any real number value. The Planck scale provides the deepest expression of this granularity. The Planck length, approximately 1.6616 times 10 to the minus 35 meters, and the Planck time, approximately 5.39 times 10 to the minus 44 seconds, represent the scale at which our current equations for space and time lose their meaning. Below the Planck length, no measurement is possible in principle, not merely in practice. Below the Planck time, no event is distinguishable from any other. These are not limits set by our current technology. They are limits built into the mathematics of quantum gravity itself. Below the Planck scale, the concepts of position, duration, and distance break down. Many theoretical approaches to quantum gravity, including loop quantum gravity, developed by Carlo Rovelli and Lee Smolin in the late 1980s, suggest that spacetime itself is discrete at this scale. Not a smooth continuum, but a kind of granular foam, a network of Planck-scale cells below which space simply has no further structure. Think about what this means in computational terms. A continuous, infinitely divisible space would require an infinite amount of information to specify the position of any particle within it. You would need an infinitely precise real number. An infinitely precise real number takes infinite information to store. No finite computation could handle a continuous universe. But a discrete universe with a minimum cell size has a finite number of states per unit volume. The universe, if space is discrete at the Planck scale, has a finite information density. Finite information density means the universe can, in principle, be computed. This is not proof of computation, but it removes an obstacle that continuous space would have presented. Then there is the speed of light. It is not just a property of electromagnetic radiation. It is the maximum speed at which any information, any causal influence, any physical effect can propagate from one point in space to another. This is a hard limit built into the structure of spacetime by special relativity, and it applies universally. Nothing with mass can reach it, and nothing can exceed it. In the language of computing, this is a clock speed, the rate at which causal information can travel across the computational substrate. A finite clock speed is exactly what you would expect if the universe were running on a finite substrate, not as an arbitrary design choice, but as a necessary consequence of the fact that information can only propagate so quickly through whatever is doing the computing. The observation dependence of quantum mechanics is the third suggestive feature and also the most treacherous to interpret. Before a quantum system is measured, it exists in superposition, multiple possible states simultaneously with probabilities assigned to each. After measurement, it resolves to one. The unobserved quantum system is in a precise technical sense indefinite. This has a suggestive resemblance to how a sophisticated simulation might work. You would not compute the properties of regions that are not being observed because that computation would be wasted. You render only what is needed. This is how modern three-dimensional video games manage their resources. Terrain outside the player's view is not rendered in detail, existing only as compressed data that will be expanded when the player approaches. I want to be very clear about where this analogy runs out because it is one of the places where the argument is most frequently oversold. The quantum measurement problem is a real and deep problem, but there are multiple interpretations of quantum mechanics that explain the appearance of observation dependence in entirely different ways. The Copenhagen interpretation treats measurement as a physical collapse of the wave function, which does resemble lazy rendering, but the many worlds interpretation says that no collapse occurs. Every possible outcome is realized in a separate branch of a universally branching wave function, all of which are equally real. In the many worlds picture, everything is computed everywhere all the time. There is no efficiency gained from observation. Pilot wave theories say the particle has a definite position all along, guided by a wave that is itself real and which fills all of space. Relational quantum mechanics says the wave function is not about physical states at all, but about the information one system has about another. These interpretations make identical experimental predictions. Nobody knows which one is correct, or whether correct is even the right frame for interpreting mathematical formalisms. The fine-tuning of the constants of nature is the fourth and most discussed piece of physical structure that refuses to be explained away. The standard model of particle physics contains approximately 25 fundamental constants. The masses of the quarks and leptons, the coupling strengths of the four fundamental forces, the cosmological constant. These constants are not predicted by the theory from first principles. They are measured experimentally and then inserted as parameters. And when physicists ask what would happen if these constants were even slightly different, the answer is consistently nothing remotely like us or like any kind of complex structure. The cosmological constant, the energy density of empty space, must be tuned to a precision of 1 part in 10 to the power of 120 in order to produce a universe that expands slowly enough for galaxies to form, but not so slowly that it collapses back on itself. This number, 10 to the 120, is so incomprehensibly large that even physicists accustomed to extreme numbers find it difficult to absorb. The strong nuclear force must be within a few percent of its actual value for carbon to be produced in stars through the triple alpha process that Fred Hoyle predicted in 1953. The ratio of the electromagnetic force to gravity must lie within several orders of magnitude of its actual value for atoms to be stable and for stars to burn steadily enough to support planetary systems for billions of years. These are not approximate constraints. They are tight, multiple, and independently derived. The mainstream physical explanation for this fine-tuning is the multiverse combined with the anthropic principle. If there are an enormous or infinite number of universes, each with different values of the constants, then we inevitably find ourselves in one of the rare ones compatible with our existence, simply because only those rare ones produce observers capable of asking the question. This is the preferred explanation among most working cosmologists because it requires no external agency and fits naturally with eternal inflation, the cosmological scenario in which inflating spacetime continuously spawns new bubble universes with different vacuum energies and thus different effective constants. But the multiverse has a deep problem. It is currently and possibly permanently untestable. We cannot observe or interact with the other universes. We cannot confirm that they exist. The simulation hypothesis offers an alternative explanation for fine-tuning that is equally untestable but philosophically distinct. The constants are set by whoever or whatever is running the simulation, chosen to produce the outcome the simulator desires, which might be complexity or life or consciousness or simply a universe interesting enough to be worth running. This is not evidence for simulation. It does not make simulation more probable than the multiverse. But it demonstrates that fine-tuning, which seemed to be evidence against any kind of designed or computational universe because it required such extreme precision, is actually exactly what you would expect in a designed or computational universe. The anomaly dissolves when you change the framework. Most discussions of the simulation hypothesis treat it as permanently beyond experiment, an unfalsifiable claim that lives in philosophy rather than physics. This is largely correct, but not entirely. In 2012, a team of physicists made a genuine attempt to identify a testable signature that would distinguish at least some versions of the simulation hypothesis from a real universe. The team was led by Silas Bean, then at the University of New Hampshire and working at the Institute for Nuclear Theory in Seattle, along with Zora Davuti, a graduate student at the University of Washington, and Martin J. Savage, a professor of physics there. Their paper, Constraints on the Universe as a Numerical Simulation, was posted to arXiv in October 2012 and subsequently published in a refereed journal. It is a careful, technically sophisticated piece of work, and it deserves more serious attention than it usually receives in popular discussions. Their starting point was the physics simulation technique they knew best, lattice quantum chromodynamics, or lattice QCD. This is the computational method that physicists actually use to simulate the strong nuclear force, the force binding quarks together inside protons and neutrons. In lattice QCD, you divide spacetime into a four-dimensional grid and compute the interactions of quarks and gluons at each node of the grid. The technique works, but it is extraordinarily computationally expensive. Simulating even a tiny volume of space, far smaller than a proton, for a fraction of a second requires the most powerful supercomputers in the world running for months. Bean and his colleagues reasoned by extrapolation. If our current simulations use a lattice with some spacing, and the universe itself were a simulation of this type running on some vastly more powerful substrate, then the universe would also have a lattice spacing, a minimum cell size for the grid of computation. That lattice spacing would impose a preferred set of directions in space, because a cubic lattice has three principal axes that are physically distinct from diagonal directions in a way that a continuous rotationally symmetric space is not. This breaking of rotational symmetry, even if tiny, would leave a physical signature. A place to look, they argued, was ultra-high energy cosmic rays, particles arriving from deep space with energy so extreme that their existence is itself surprising. The GZK limit, predicted in 1966 by Kenneth Greisen and independently by Georgy Zatsepin of Moscow, sets an upper bound on the energy of cosmic rays that can travel cosmological distances. Because above roughly 10 to the 19th electron volts, particles interact with the cosmic microwave background radiation and lose energy rapidly. Cosmic ray detectors do observe a cutoff roughly where the GZK prediction puts it. But in a lattice-based simulated universe, the lattice spacing would impose an additional energy cutoff, and that cutoff would be slightly different depending on the direction from which you observe the cosmic rays. The angular distribution of the highest energy cosmic rays would show a subtle preference for directions aligned with the lattice axes. No such anisotropy, no such preferred direction has been detected. The Pierre Auger Observatory in Argentina, which is the world's largest cosmic ray detector and which has been collecting data since 2004, observes the highest energy cosmic rays arriving from all directions without the kind of systematic directional preference the lattice model would predict. Does this prove that the universe is not a simulation? No. The paper's own conclusions are more careful. It constrains one specific type of simulation architecture. If the universe is simulated on a lattice, the lattice spacing must be smaller than the current experiments can probe in this way, at least 10 to the 11th GeV in energy units, which corresponds to a length scale well below what is experimentally accessible. A simulation with a finer grid or with a different geometry than a cubic lattice, or with a simulation architecture that doesn't produce lattice-style artifacts, would leave no detectable signature in this search. Sabine Hossenfelder, a German theoretical physicist, formerly at the Frankfurt Institute for Advanced Studies, has made this point with characteristic directness. Any simulator sophisticated enough to create a universe that has remained physically consistent for 13.8 billion years is presumably sophisticated enough to choose a simulation architecture that doesn't produce obvious lattice artifacts in cosmic ray distributions. The absence of the signal tells you something about naive lattice models. It tells you nothing about the simulation hypothesis in general. A sufficiently advanced simulation would look exactly like a real universe from the inside, because its architecture would be chosen, if it were chosen by anything, to avoid detectable artifacts. This is the central scientific objection, and it is serious. An unfalsifiable hypothesis is not a scientific hypothesis in the strict sense. It may still be philosophically meaningful and it may still be true, but it cannot be the subject of experimental inquiry in any straightforward way. The simulation hypothesis, at its most general, is structured in a way that makes it immune to experimental refutation. Any observation is equally consistent with being in a simulation as not being in one, because a sufficiently sophisticated simulation would produce exactly the observations a non-simulated universe would produce. This is not a feature. It is a problem. But the unfalsifiability objection proves less than it is often taken to prove. Unfalsifiability is the bar for being a scientific hypothesis in the experimental sense. It is not a bar for being true. The existence of other minds is unfalsifiable in a strict sense. You cannot step outside your own consciousness to verify that other people have genuine subjective experience rather than being philosophical zombies. The interpretation of quantum mechanics is currently unfalsifiable. The different interpretations make identical predictions. The multiverse, the most popular alternative to fine-tuning, is unfalsifiable. Some of the deepest questions in human inquiry shade into territory where experiment cannot directly reach, and the simulation question is genuinely one of them. Treating unfalsifiability as a decisive refutation is too simple. In November 2025, a team of physicists published what they described as a mathematical proof that the universe cannot be a computer simulation. The claim attracted significant attention and was reported widely, and it deserves a careful examination, both for what it actually establishes and for where its argument runs into difficulty. The paper was led by Mia Faisal, an adjunct professor at the University of British Columbia, Okanagan's Irving K. Barber Faculty of Science, and co-authored with Lawrence Krauss at Arizona State University, Arshid Shabani, and Francesco Marino. It was published in the Journal of Holography Applications in Physics, and its central argument draws from some of the most foundational mathematics of the 20th century. In 1931, the Austrian mathematician Kurt Gödel published two incompleteness theorems that permanently changed the foundations of mathematics. Gödel had set out to investigate whether mathematics could be formalized completely, whether starting from a finite set of axioms and rules, every true mathematical statement could in principle be proven. The answer he showed was no. Any consistent formal system powerful enough to express basic arithmetic contains true statements that cannot be proven within that system. It is not that we lack the cleverness to find the proofs. The proofs do not exist. The statements are true, but the formal system cannot reach them. A second theorem showed that any such system cannot prove its own consistency. Gödel's result was experienced by the mathematical community as a kind of earthquake. The dream of a complete and self-certifying mathematics was permanently over. Faisal and his colleagues applied Gödel's insight to physics. Any simulation is by definition algorithmic. It runs a program, a finite set of instructions applied step by step to a finite or infinite computational substrate. But if the universe contains physical truths of a Gödelian character, truths that are real features of physical reality, but that no algorithm can compute or verify, then no simulation could reproduce them. The universe would contain more than any computation can express. Therefore, the universe cannot be a simulation. Lawrence Krauss described the implication. The fundamental laws of physics cannot be contained within space and time because they generate them. A complete and consistent description of reality requires something deeper, a form of understanding known as non-algorithmic understanding. Faisal's own statement was equally direct. Any simulation is inherently algorithmic, but since the fundamental level of reality is based on non-algorithmic understanding, the universe cannot be and could never be a simulation. This is a striking argument, and it was widely reported as a decisive refutation, but it attracted immediate and substantive technical criticism, and the criticism identifies a real gap in the reasoning. The most precise version of the objection was published in December 2025 by Evan Redden at Western Governors University in a comment paper on ArcCiv titled Provability versus Execution. A comment on consequences of undecidability in physics on the theory of everything. Redden's objection is conceptually simple but technically precise. Gödel's incompleteness theorems are about provability, what statements can be proven within a formal system. They are not about computability or execution, what processes can run and produce outputs. A simulation does not need to prove every true statement about itself. It simply needs to run, processing each step according to its rules, without being derailed by the existence of truths it cannot prove. The existence of unprovable truths within a formal system does not cause the system to fail or halt. It simply means that certain questions posed to the system in the right way will produce no output. The computation will run forever without terminating, which is exactly the behavior Alan Turing described when he proved the halting problem undecidable in 1936. Redden illustrated this with Conway's game of life, a cellular automaton invented by the mathematician John Horton Conway in 1970. The game of life runs on an infinite grid of cells, each of which is either alive or dead, according to 4 simple rules applied at each time step. Despite its simplicity, the game of life is Turing complete. Given enough space and time, you can build within it any computation that any computer can perform. There are undecidable questions about the game of life, questions that have definite answers, but that cannot be resolved by any finite algorithm. For example, the question of whether a given initial configuration will eventually produce a particular pattern is in general undecidable. But this does not prevent the game of life from running. The simulation executes step by step, and the undecidable questions remain open, undisturbed, the mechanics of the computation. A simulation of a universe would be in exactly the same position. Undecidable physical truths would exist. The simulation would keep running regardless. There is a further difficulty with Feisel's argument that is worth naming. The argument assumes that non-algorithmic understanding is required to describe physical reality. But what is non-algorithmic understanding? If it is a property of a physical process, then it is itself a physical process. And the question of whether a simulation could run it simply reemerges at a different level. If it is something outside any physical or computational process, then it is not clear what it is or how it interacts with physical reality. The argument may establish that a simple algorithmic theory of everything is impossible, which is consistent with what mathematicians already knew from Gödel's work. It does not clearly establish that the universe itself is not a simulation. In December 2025, David Wolpert at the Santa Fe Institute published a different mathematical approach to the simulation question in the Journal of Physics Complexity. Rather than trying to prove or disprove the hypothesis, Wolpert formalized what it actually means for one universe to simulate another. His analysis found that the intuitive concept of simulation fragments into multiple distinct mathematical relationships, some of which allow for remarkable structures, closed loops of simulation, where universe A contains a computer that simulates universe B, which contains a computer that simulates universe A, with neither being more real than the other. Wolpert's framework does not settle the question of whether we are in a simulation, but it illustrates how far the question remains from having a clean mathematical resolution in either direction. The architecture of the problem is more complex than any simple proof or disproof has so far captured. Even among the scientists who take the computational universe hypothesis seriously, there is one aspect of it that generates the most profound discomfort, and it is not the physics. It is the question of consciousness, whether a computation can produce genuine subjective experience, and what it would mean for the universe's inhabitants if the universe were indeed a running program. If the universe is a simulation, what is the status of the minds within it? There are 2 broad possibilities, and they lead to radically different conclusions about the nature of experience, ethics, and the significance of existence. The first possibility is that consciousness is a property of certain kinds of information processing, independent of the physical substrate on which that processing runs. In this view, it does not matter whether the information processing is implemented in biological neurons, in silicon transistors, or in the operations of a simulation running on some incomprehensible external computer. What matters is the pattern of processing, the functional architecture of the system. If the right kind of information processing is present, consciousness is present. Simulated minds would be genuine minds. Simulated suffering would be genuine suffering. The second possibility is that consciousness is substrate dependent in a way that no computation can replicate, that biological neurons or physical processes of the right kind produce genuine experience through some mechanism that is not captured by functional description alone. Um, and that a computational process, however detailed, however perfectly it reproduces the functional behavior of a conscious system, would produce something that looks conscious from the outside but is not experiencing anything from the inside. In this view, there is no one home in a simulation. David Chalmers, who is the university professor of philosophy and neural science at New York University, and who is the philosopher most responsible for defining the contemporary terms of this debate, has argued for the first view throughout his career. Chalmers coined the phrase the hard problem of consciousness in 1995 to describe the question of why any physical process produces subjective experience at all, rather than just performing its functions in the dark. He spent decades arguing that this problem is distinct from all the functional and behavioral questions that neuroscience can, in principle, answer, and that it represents something genuinely unexplained by any current physical or computational theory. In his 2022 book, Reality Plus, Virtual Worlds and the Problems of Philosophy, published by W. W. Norton, Chalmers brought this framework to bear directly on the simulation hypothesis. His central argument is that simulated worlds are genuine realities, not pale imitations of some more authentic reality. The objects in a simulated world are real objects. The experiences in a simulated world are real experiences. If you are living in a simulation, your experiences are no less real than they would be in a base reality, because what makes an experience real is the experience itself, not the substrate generating it. The redness of red is real in your experience, regardless of whether that experience is generated by biological neurons or by computational processes. Chalmers calls this virtual realism. Virtual worlds are genuine, not deficient. If Chalmers is right, then the simulation hypothesis has moral implications that are not at all reassuring. A civilization running detailed simulations of conscious minds is creating conscious beings. Those beings can suffer, flourish, hope, grieve, and search for meaning in exactly the way that we do. The ethical weight of that is substantial. Nick Bostrom has suggested that if the third branch of his trilemma is true, one of the rational existential anxieties it generates is that whoever runs the simulation might someday choose to turn it off, not maliciously, but for the same reason you close a program you no longer need. The entire history of conscious experience, every moment of joy and grief and discovery that has ever occurred inside the simulation would end at a computational decision made outside it. But Chalmers' substrate independence is not an established fact. It is a philosophical position, specifically a form of functionalism about mind, and it is contested. John Searle, the philosopher who designed the famous Chinese room argument in 1980, has argued that functional equivalence is not sufficient for consciousness. A system that processes information in the same way as a mind might still lack the biological causal structure that produces genuine understanding and experience. Roger Penrose, the Oxford mathematician who shared the 2020 Nobel Prize in Physics for his work on black holes, has argued in books like The Emperor's New Mind and Shadows of the Mind that consciousness involves non-computable processes, possibly related to quantum gravity at the level of microtubules in neurons, and that no computer, however powerful, could reproduce genuine human thought. Penrose's specific mechanism has been criticized on various grounds, but his broader point that consciousness might not be computationally reproducible remains a serious philosophical position. We simply do not know. The hard problem of consciousness has remained hard for 30 years since Chalmers named it, and there is no clear scientific consensus about whether a computational process can produce genuine experience. This uncertainty cuts both ways in the simulation debate. It means we cannot be confident that simulated minds would be genuine minds, but it also means we cannot be confident that they wouldn't be. And that uncertainty, hovering over one of the most consequential questions the hypothesis raises, is itself a measure of how far we are from a settled answer. There is a set of objections to the simulation hypothesis that come not from philosophy or from mathematics, but from the physics of computation itself. The simple, brutal question of what it would actually cost in physical resources to simulate a universe like ours. These objections are among the most concrete, and they deserve to be taken seriously because they put hard numbers on what an otherwise abstract hypothesis would require. Franco Vatsa, an astrophysicist at the University of Bologna with expertise in the large-scale structure of the universe, published a detailed analysis of these constraints in a 2025 paper in Frontiers in Physics. His starting point was to estimate the information content of the observable universe at various levels of resolution and to ask what computational resources any simulation of our universe would require. The observable universe contains roughly 2 times 10 to the 80 protons. Each proton's quantum state involves a description in terms of many coupled quantum degrees of freedom. To simulate a single proton at the resolution of quantum chromodynamics, the theory that describes its quark and gluon constituents requires computational resources that are already at the edge of what current supercomputers can manage for a tiny fraction of a second. To extend this to the full content of the observable universe for 13.8 billion years would require a computer vastly larger than any physical system within the observable universe. Vaz's paper notes that even conceding the most optimistic assumptions about the simulator's computational efficiency, Planck-scale black hole computers operating at the Landauer limit of thermodynamic efficiency, the information content of the observable universe still exceeds what any physically conceivable computation within our observable horizon could produce. This is a powerful objection, but it has a standard response that the simulation community offers. The simulation might not need to simulate the entire universe at full resolution. It might use lazy evaluation, only computing in detail the regions that are actually interacting with observers and leaving the rest as compressed representations to be expanded on demand. The universe from this perspective might look full and detailed from the inside, while being computationally sparse on the outside, because only the parts that are being rendered by observation are computed in detail. This response is not obviously wrong, but it creates a tension with what we know about physics. Quantum mechanics tells us that the universe maintains coherent quantum states even in regions that no observer has ever interacted with. The cosmic microwave background radiation, the afterglow of the Big Bang, carries information about temperature fluctuations in the early universe that no conscious being has ever observed in regions billions of light years away from any life. If the simulation is only computing regions that are observed, it faces a problem. Quantum mechanics says that the unobserved regions have definite coherent quantum states that can be verified by observations made later. A simulation that computes those states only when they are eventually observed would need to ensure consistency with all the physical constraints that would have accumulated if the states had been real all along. This is in principle possible, but it requires a simulator that is tracking the logical consequences of every unobserved state continuously, which is not obviously cheaper than just computing them directly. Hassenfelder has made this point with unusual precision. The simulation hypothesis, she argues, does not just require that the simulator is smart. It requires that the simulator can efficiently manage the quantum correlations between observed and unobserved regions, can identify which parts of the simulation are being observed and which are not, and can always produce consistent results when observations are made. This is a vastly more difficult problem than it sounds. Quantum entanglement means that distant regions can have correlated states, and maintaining those correlations while simulating only one region at a time is not straightforwardly possible. The simulator would need to track the quantum state of the entire universe, even to compute a small part of it accurately. These computational constraints do not rule out the simulation hypothesis because we have no idea what laws of physics govern the simulator's universe. And a physics very different from ours might allow computational resources of a kind we cannot imagine. But they do establish that the simulation hypothesis is not free. It requires a physical infrastructure that, by our best current understanding, would be more complex than the thing it simulates. Whether that is physically possible depends on physics we don't know. There is a version of this question that goes deeper than the simulation hypothesis in its standard form, and it comes from taking seriously what physics has already established about the relationship between reality and mathematics. The physicist Max Tegmark at MIT has developed this into a full philosophical position, which he calls the mathematical universe hypothesis, and which he laid out in his 2014 book, Our Mathematical Universe: My Quest for the Ultimate Nature of Reality. Tegmark's starting point is an observation that is easy to state but difficult to absorb. Modern physics does not merely describe the universe with mathematics. The entities physics identifies as fundamental, wave functions, quantum fields, space-time metrics, Hilbert spaces, are mathematical objects, not physical things that happen to be described by mathematical equations. Mathematical structures that are identified with physical reality. An electron's quantum state just is a vector in a Hilbert space. The electromagnetic field just is a particular kind of fiber bundle. Space-time just is a pseudo-Riemannian manifold. There is no electron underneath the mathematics. No physical substrate that the mathematics is pointing at. The mathematics is all there is as far as any experiment can determine. If this is right, Tegmark argues, then the distinction between mathematical structures that exist and mathematical structures that we happen to inhabit is not a meaningful distinction. All mathematical structures that are self-consistent exist in the same sense that ours does. There is nothing that makes our particular mathematical structure more real than any other. We happen to be in this one because this one produces observers capable of finding themselves in it. The structure of our universe is a specific mathematical object, the standard model coupled to general relativity plus whatever completes quantum gravity, and it is as real as any other mathematical object. No more, no less. The mathematical universe is not a simulation exactly. It is something more radical. Reality is itself mathematical, not represented by mathematics. The connection to the simulation hypothesis is that if reality is fundamentally mathematical, then the distinction between being computed and really existing begins to dissolve. A mathematical structure that is computed and a mathematical structure that exists are in Tegmark's framework the same thing. There is no substrate of real physical reality underneath the mathematics that distinguishes the genuine article from a computation. If you could perfectly compute our universe's mathematical structure, you would not be simulating reality from outside. You would be instantiating reality from the same level. This is a minority position among physicists, and it has been criticized from multiple directions. Some argue that mathematics as a discipline is a human construction, not an autonomous realm of objects with independent existence. Others argue that the claim that all mathematical structures exist is so broad as to be vacuous. It explains nothing about why we find ourselves in this particular structure rather than some other. The philosopher Tim Maudlin has argued that Tegmark conflates two very different senses of exist: the mathematical sense in which a consistent structure is well defined, and the physical sense in which something is actually present in the world. But whatever its ultimate validity, the mathematical universe hypothesis clarifies something important. The simulation question may be not just unanswered, but unanswerable in any empirical sense, because the answer depends on a distinction between really existing and being computed that may not correspond to anything physically testable. If the universe is a mathematical structure and mathematical structures just exist, then asking whether this mathematical structure is really existing or merely being computed is like asking whether the number 7 is really 7 or just a computation of 7. The question may be malformed. One of the more recent developments in the physics of holography has added a new and technically striking element to this entire discussion. In 2015, 3 physicists, Ahmed Al-Mahiri, Shi Dong, and Daniel Harlow, published a paper that drew a precise analogy between the holographic dictionary of ADS-CFT, the translation between bulk spacetime and boundary quantum theory, and a well-developed technique from computer science, quantum error correction. Quantum error correction is the science of protecting quantum information from the inevitable noise and decoherence that threatens any physical implementation of quantum computation. The central idea is that you do not store quantum information in a single qubit, which might be disrupted by a single error. Instead, you spread the information redundantly across many qubits in a pattern that allows you to detect and correct errors by measuring the whole rather than any individual part. The patterns used for this, called quantum error correcting codes, have specific mathematical properties that relate the information stored, the logical qubits, to the physical qubits that carry it. Almhiri, Dong, and Harlow found that the way spacetime information is encoded in the boundary theory in ADS-CFT has exactly the structure of a quantum error correcting code. The information about what happens in the interior of the spacetime is encoded on the boundary in a redundant, distributed way. You can recover the full interior physics from any sufficiently large piece of the boundary, and losing small pieces of the boundary does not destroy the interior information. The holographic dictionary is not just a mathematical correspondence. It has the specific structure of a robust information storage system. This is remarkable for several reasons. Error-correcting codes are designed. They are the product of deliberate engineering chosen to protect information against specific types of noise. The fact that the relationship between bulk spacetime and boundary quantum theory has this specific error-correcting structure is not something that was put in by hand. It emerges from the physics of quantum gravity. And it means that the universe, or at least the idealized version of the universe that ADS-CFT describes, stores its spatial information in the way that a competent engineer would choose to store important information redundantly, distributedly, robustly. Patrick Hayden at Stanford University and colleagues have extended this work, showing that the error-correcting structure of holography is connected to the phenomenon of black hole information. The question of whether information that falls into a black hole is eventually returned to the universe in Hawking radiation. The Hayden-Preskill paper of 2007 by Hayden and John Preskill at Caltech had shown that information thrown into an old black hole, one that has already radiated away more than half its entropy, is returned almost immediately in highly scrambled form in the Hawking radiation. This means that black holes are extraordinarily efficient information scramblers, and the structure of that scrambling is related to the error-correcting structure of holography. The universe seems to be very good at not losing information in a way that looks to a computer scientist like it was designed to be. In July 2026, new results from Quera, a research group using quantum simulation to probe holographic physics, demonstrated that quantum entanglement patterns on a two-dimensional system can reproduce gravitational physics in 3 dimensions in ways that are consistent with the error-correcting structure Almhiri, Dong, and Harlow identified. This is still work in a specific theoretical framework, not direct measurement of the real universe. But it continues to establish that the mathematical structure connecting information and spacetime is robust and experimentally testable in controlled analog systems. The bridge between the abstract mathematics of holography and physical experiment is being built slowly from both ends. The title of this script promises to examine a theory that scientists don't want to talk about, and it is worth being precise about what that means and what it doesn't mean. Most working physicists don't want to talk about the simulation hypothesis for reasons that are practical, not epistemic. The hypothesis in its most general form makes no testable predictions and therefore generates no publishable experimental physics. Time spent thinking about it is time not spent on problems that can actually be solved and published and funded. Physics careers are built on contributions to research programs that produce results. The simulation hypothesis at present is not that kind of program. There is also a social dimension in a field where precision and rigor are the primary virtues. Association with a hypothesis that is widely perceived as speculative or even fringe carries a professional cost. Physicists who publicly engage with the simulation hypothesis risk being seen as more interested in science fiction than in science. This is an unfair association given that the hypothesis connects to genuinely fundamental questions in physics. But social perception is not always fair, and professional caution is rational. But there is a third and more interesting source of discomfort, one that is rarely named explicitly. The simulation hypothesis, if true, would dissolve the foundational assumption of physics as it has been practiced for 4 centuries, that it is studying the universe as it actually is, discovering laws that are not contingent on any external agency, finding a reality that simply is the way it is because of nothing but itself. The laws of physics in this view are not rules someone decided on. They are the way things are, and finding them is the deepest form of knowledge available to any mind. The simulation hypothesis threatens this entire picture. If the universe is computational, the laws of physics are the rules of the simulation chosen by whoever or whatever is running it, for whatever reasons motivated the choice. The constants of nature are parameters in a program. The history of the universe is a run of a computation that could in principle have been set up differently. Physics, instead of discovering the fundamental structure of reality, would be reverse engineering someone else's code. An important enterprise, perhaps, but a fundamentally different one. Most physicists find this vision deeply unappealing, and I think it is worth being honest about how much that aesthetic dislike shapes what gets taken seriously in professional discourse. The desire to be studying something fundamental rather than something contingent is a real desire, and it has real effects. It is worth separating the epistemic question, is the simulation hypothesis true, from the aesthetic one, would it be disappointing if it were? These are different questions, and conflating them leads to motivated reasoning. Among the physicists who have been willing to sit with the discomfort publicly are some significant figures. Max Tegmark, as already noted, has developed the mathematical universe framework that partly dissolves the question. Neil deGrasse Tyson, in a widely circulated 2016 panel discussion, estimated the probability of the simulation hypothesis at 50-50 or better, based primarily on the acceleration of computing technology. James Gates Jr., a distinguished string theorist at Brown University, has written about finding error-correcting code structures, specifically adinkras, embedded in the mathematics of supersymmetry, and has suggested cautiously that this deserves attention as a possible simulation signature. Elon Musk has said on multiple occasions that he believes the probability of not being in a simulation is roughly 1 in billions, though Musk's views on many technical matters need to be weighed against his tendency to confident pronouncement. The serious version of the engagement comes from people who are careful about what the evidence actually shows and careful about the difference between a suggestive pattern and a proof. Gates's observation about adinkras is genuinely interesting. The error-correcting codes he identified embedded in supersymmetric equations were not put there intentionally, and their presence in the fundamental mathematics of particle physics is not obviously explained. But it is also not clearly simulation evidence because mathematics is full of structures that appear in multiple contexts for reasons that are combinatorial rather than cosmic. The same codes appear in many places in mathematics. Finding them in physics does not definitively mean they were put there by a programmer. After traversing all of this ground, it is worth returning to Earth and stating as plainly as possible what the actual epistemic situation is. Not the excited version, not the dismissive version, but the honest one. We know that the universe has several features that are consistent with a computational description and would be required or expected in certain kinds of computational systems. These include the quantization of energy, charge and angular momentum, a maximum speed of information propagation, the holographic encoding of spatial information on boundaries, and a Planck scale structure that imposes a minimum cell size on physical description. These are established features of physics. They do not prove simulation, but they are not random and they fit a computational picture. We know that the holographic principle, and specifically the ES-CFT correspondence, proven mathematically by Juan Maldacena in 1997, establishes that three-dimensional spacetime with gravity can be exactly described by a two-dimensional quantum system without gravity. This is not the simulation hypothesis, but it is the same category of result. The three-dimensional character of the world we experience is not the most fundamental thing about it. Something lower dimensional knows everything about it. We know that Bostrom's trilemma is logically valid. At least one of three things must be true. Civilizations like ours usually go extinct before reaching simulation capability. Simulation capable civilizations usually choose not to simulate, or we are almost certainly in a simulation. No one has found a way to reject the trilemma's logic, though many have questioned its premises. Each branch of the trilemma is significant on its own terms, and none of them is obviously true. We know that specific testable versions of the simulation hypothesis, such as the lattice model analyzed by Silas Bean, Zoré Davoudi, and Martin Savage in 2012, make concrete predictions that have not been confirmed. The directional anisotropy in ultra-high energy cosmic rays predicted by the simplest lattice simulation model has not been observed. This constrains some architectures, but says nothing about the hypothesis in general. We know that the 2025 argument by Mia Feisel, Lawrence Krauss, and colleagues that Gödelian incompleteness proves the universe cannot be a simulation has been contested on the grounds that incompleteness limits provability, but not computability, and that a running simulation does not need to prove every true statement about itself. The argument is a genuine contribution to the debate, but is not a settled refutation. We know that the question of whether computation can produce genuine consciousness is unresolved. The hard problem of consciousness has resisted solution for three decades, and there is no scientific consensus on substrate independence. Without knowing whether computation can generate genuine experience, we cannot assess the most morally significant implications of the simulation hypothesis. And we know that the question is not pseudoscience. It is speculative in the sense of reaching beyond what evidence currently establishes, but it connects to established physics, generates genuine technical research, and has a history of engagement by serious scientists and philosophers. The questions it raises are questions that responsible intellectual life cannot simply ignore. The simulation hypothesis is, at its core, a modern version of a question that philosophy has asked in various forms for as long as philosophy has existed. Plato's allegory of the cave described prisoners who see only shadows on a wall and mistake them for reality. Never aware of the world beyond that produces the shadows. René Descartes, in his Meditations on First Philosophy, published in 1641, asked whether an evil demon might be deceiving him about the entire nature of the world, feeding him illusory sensations of a reality that does not exist. George Berkeley, the 18th century philosopher, argued that matter does not exist at all and that reality is entirely mental. The universe consists of minds and their ideas with no physical substrate underneath. The simulation hypothesis is the technological update to this ancient philosophical puzzle. Instead of an evil demon, there is a programmer. Instead of a world of pure ideas, there is a digital substrate. Instead of Descartes' solitary doubt, there is Bostrom's probabilistic trilemma. The specific form has changed, shaped by the language of computing and the content of modern physics. But the question underneath, what is the relationship between experience and the ground of reality that produces it, remains the same question it has always been, and it remains after 24 centuries of philosophical work and 3 centuries of physics unanswered. This persistence is itself significant. Questions that have no genuine purchase on reality tend to dissolve over time. When an argument has a decisive answer, the question it poses stops being asked. The hard problem of consciousness has not dissolved. The question of why there is something rather than nothing has not dissolved. The question of what, if anything, underlies the mathematical structure of physics has not dissolved. The simulation hypothesis belongs to this family of questions, ones that point at something real that our concepts and methods have not yet found a way to fully grasp. John Archibald Wheeler, who spent the final decades of his life developing the is-it from bit program, was not trying to argue that the universe is a simulation in the Bostrom sense. He was asking whether the concept of physical reality as we have understood it since Newton needs to be replaced by something in which information and observation are not consequences of the physical world, but conditions for it. His point was not that the universe is fake. It was that the category physical stuff might not be the fundamental category we have assumed it to be, and that something more like information being exchanged between systems might be closer to the bottom. The ongoing work in quantum information, quantum error correction, and quantum gravity is slowly clarifying this picture without yet resolving it. The universe's structure at the deepest level accessible to current theory is increasingly described in the language of quantum information, qubits, entanglement, quantum channels, error-correcting codes. Whether this language is a useful description of something more fundamental, or whether the universe's information in a deeper sense is the current frontier. Let me try to do something that is rarely done in discussions of this topic. Think carefully and honestly about what would actually follow if the simulation hypothesis turned out to be true. Not in the science fiction sense of the Matrix, but in the more rigorous sense of a universe whose physical laws are implemented by some computational substrate external to what we normally call physics. The most common reaction to this possibility is despair. If everything is a simulation, nothing is real. Nothing matters. This reaction is understandable, but I think wrong on multiple counts. Begin with the question of realness. If the simulation hypothesis is true, and Chalmers' substrate independence of consciousness is also true, then every experience that has ever occurred inside the simulation is genuinely real as any experience could be. The child's laughter, the scientist's insight, the grief of loss, the love between people. These are not diminished by being implemented in a computation rather than in base physics any more than music is diminished by being stored as digital files rather than as grooves in vinyl. The pattern is the thing, not the substrate. The laws of physics would remain exactly what they are. The history of science would remain exactly what it is, a long, hard-won process of discovering the mathematical structure of the universe, which would remain the mathematical structure of the simulation. The fact that the laws are implemented rather than bare might feel like a deflation, but it is not. Implemented laws are still laws. They still govern everything inside the simulation with exactly the precision and universality that physics has always ascribed to them. Gravity would still pull. Light would still travel at the same speed. The second law of thermodynamics would still hold. Nothing about the practice of science or about the knowledge it produces would change. What would change is the answer to the deepest version of the question. Why is there something rather than nothing? The physicist's form of this question, why does the universe exist and why does it have these laws rather than some other laws, would be partly answered. The universe exists because a simulator runs it. And it has these laws because those are the laws the simulator chose. But this moves the question back a level rather than answering it. Why is there a simulator? And why does the simulator's universe have the laws that allow the simulator to exist? The regress continues. The deepest question of existence does not dissolve, it propagates. There is also the question of meaning and purpose, which is perhaps the most emotionally fraught. A simulator who created our universe may have done so for any reason or no reason. There is nothing in the structure of the hypothesis that implies the simulator cares about us, is benevolent toward us, or has any opinion about the choices we make. The simulation is not necessarily meaningful in a cosmic sense, just as a game is not necessarily meaningful beyond the meaning the players bring to it. The absence of cosmic meaning, however, is not the same as the absence of any meaning. Meaning, in the most defensible account, arises from the choices and relationships and experiences of conscious beings, not from the ultimate metaphysical substrate in which those conscious beings exist. If we are the source of our own meaning, then the computational status of our universe changes nothing about the meaning we make. The simulation hypothesis has been with us as a serious philosophical question for more than 2 decades, and as a serious physical question for a somewhat shorter time. It shows no sign of dissolving. The reasons for this persistence are worth understanding. First, the development of quantum computing is giving us new and concrete intuitions about what it costs to simulate quantum physics and where the limits of simulation capacity lie. Current quantum computers, though still limited, are able to simulate small quantum systems in ways that classical computers cannot. As quantum computers scale up, physicists will gain practical experience with the question of what it costs to simulate quantum mechanics at various resolutions and scales. This empirical knowledge will not settle the simulation hypothesis, but it will sharpen the technical questions and might generate new ideas for how to think about them. Second, the ongoing development of quantum gravity theory is pressing toward the question of what spacetime is made of at the most fundamental level, and whether the answer is anything like information. Loop quantum gravity, causal set theory, spin foam models, and the asymptotic safety program all represent different ways of approaching this question. And all of them will eventually produce more precise predictions about the Planck scale structure of spacetime that could, in principle, be tested by future experiments with sensitivity to those scales. If spacetime turns out to be genuinely discrete in a way that current theories predict, that will be an important datum for thinking about the simulation hypothesis, though it will not be decisive. Third, the mathematical and philosophical tools for thinking about the question are becoming more precise. David Wolpert's formalization of what it means for one universe to simulate another, published in 2025, is an example. It converts a vague intuition into a set of technically precise definitions, and in doing so reveals new questions and potential distinctions that were invisible before. Faisal and Krauss's argument, whatever its ultimate merits, is another. It brought mathematical logic to bear on a question that had been discussed mostly at the level of intuition, and it forced a more precise conversation about what kinds of computational processes can and cannot reproduce physical phenomena. Zohra Davoudi, who participated in the original cosmic ray paper in 2012 and has continued to work in nuclear theory at the University of Maryland, has argued in recent work that quantum simulations of specific physical systems, particularly quantum chromodynamics on small scales, might allow physicists to understand which features of physics are generic emergent properties of any quantum gravity theory, and which features would be signatures of a specific computational architecture. This is slow, careful, unglamorous work, but it represents the best current attempt to find the edge of the question, the place where it makes contact with something experimentally accessible. There is a branch of theoretical physics called digital physics that has been developing quietly and without much fanfare since at least the 1960s. Digital physics is the program of trying to reformulate fundamental physics in terms of information theoretic or computational primitives, not as a metaphor, but as a technical research agenda. Its practitioners include some serious names, though the program has never achieved mainstream acceptance, and it has often been treated with a mixture of benign neglect and occasional irritation by the larger physics community. Konrad Zuse, the German engineer and computer pioneer who built some of the earliest programmable computers in the 1940s, proposed in 1969 that the universe might be running on a discrete computational process he called the Rechnender Raum, or computing space. Zuse was not a professional physicist, and his proposal was not mathematically developed. But it was among the first serious suggestions that the universe might be literally computational rather than merely describable by mathematics that can be computed. His paper sat largely unnoticed for decades. Edward Fredkin, an American physicist and computer scientist who has worked at MIT, independently developed a similar program. Fredkin's core idea is that the universe is a finite automaton, a computational process running on a discrete substrate, processing information according to local rules at each step. He has argued with considerable technical detail that the known laws of physics can be derived as emergent properties of a sufficiently sophisticated cellular automaton, a generalization of Conway's game of life to the physics of the real world. His work has attracted intermittent attention from physicists and has been criticized for not yet producing specific testable predictions that differentiate it from standard physics. Stephen Wolfram, the physicist and computer scientist who created Mathematica and authored the controversial 2002 book A New Kind of Science, has been pursuing the most ambitious version of this program. Wolfram's Wolfram Physics Project, launched publicly in 2020, proposes that the universe can be described as a discrete rule-based hypergraph rewriting system, a graph whose nodes and edges are updated according to simple rules, with the resulting complex structure giving rise to space, time, matter, and the laws of physics as emergent phenomena. Wolfram claims to have reproduced in this framework versions of special relativity and quantum mechanics as consequences of the simple underlying rules. The reception within the professional physics community has ranged from skeptical interest to outright dismissal. Critics argue that reproducing the formal structure of physical laws in a computational framework is not the same as deriving those laws. Many frameworks can be made to look like they reproduce physics by suitable choice of rules, and the challenge is to produce a specific quantitative prediction that distinguishes the Wolfram framework from the standard one. Supporters argue that the project is in its early stages and that the formal resemblance between the emergent structures and the mathematical objects of physics is too close to be coincidental. The most technically sophisticated version of digital physics currently alive is probably the It from Qubit program, whose name deliberately echoes Wheeler's It from Bit. This research agenda aims to derive the geometry of spacetime from the quantum entanglement structure of an underlying quantum system. Mark van Ramsdonk at the University of British Columbia showed in a 2010 paper that the connectedness of spacetime in ADS-CFT is related to the entanglement between quantum systems on the boundary. Decrease the entanglement and the spacetime geometry begins to fragment as if the connections between regions are made of entanglement rather than of something more tangible. Shinsei Ryu and Tadashi Takayanagi showed in 2006 that the entropy of boundary regions is computed by the area of minimal surfaces in the bulk spacetime. A result now called the Ryu-Takayanagi formula that connects quantum information content to spacetime geometry with extraordinary precision. Jeff Pennington at the University of California, Berkeley, and Ahmed Almhairi at New York University published work in 2019 that resolved a long-standing paradox about information loss in black holes, showing that the entropy of Hawking radiation follows a page curve and recovers the original quantum information in a way that implicates the quantum entanglement structure of the spacetime geometry rather than any simple local dynamics. This resolution required understanding the interior of the black hole in terms of what is called the entanglement wedge, a region of bulk spacetime that can be reconstructed from the quantum state of a given boundary region using the same error-correcting code structure that Almhairi, Dong, and Harlow had identified 4 years earlier. What this body of work collectively suggests with enormous caveat is that the geometry of spacetime may emerge from an entanglement structure of an underlying quantum system. Spacetime is not fundamental. It is derived. The direction of travel in theoretical physics is unmistakably toward a universe in which information is more fundamental than space. There is an observation about the simulation hypothesis that is rarely made explicit, but that has the potential to reframe everything else. The anthropic constraints that make the simulation hypothesis seem plausible are exactly the same anthropic constraints that make it almost impossible to evaluate rigorously. Let me explain what I mean. Bostrom's argument relies on the observation that if simulations are possible and common, then simulated minds vastly outnumber biological minds, and therefore a randomly chosen mind is almost certainly simulated. But this counting argument applies only if we are genuinely a random sample from the space of all minds. And the problem is that we cannot be sure we are. Anthropic selection effects, the biases introduced by the fact that we can only find ourselves in a universe or simulation that allows our kind of existence, may distort the count in ways that are very difficult to reason about. This is known in philosophy as the anthropic principle applied to observer selection, and it has been developed most carefully by Nick Bostrom himself in his 2002 book, Anthropic Bias: Observation Selection Effects in Science and Philosophy, published by Routledge. The key idea is that when you are reasoning about which type of world you are likely to be in, you need to account for the fact that your existence in this world is itself a condition on the question. You cannot be in a world where you don't exist, and this tautological constraint can, if handled carelessly, lead to paradoxes and incorrect probability estimates. Suppose that simulations by their nature tend to produce fewer conscious observers per unit of computational time than biological universes. Or suppose that the proportion of simulated universes that produce long-lived complex civilizations capable of asking philosophical questions is lower than the proportion of non-simulated universes that do so. In either case, the anthropic correction would reduce the probability of being in a simulation, even when simulated minds outnumber biological ones in total. The correct reference class for the probability calculation is not all minds, but all minds like us. And defining what like us means is deeply contested. Nick Bostrom has acknowledged this problem and attempted to address it through what he calls the self-sampling assumption and the self-indication assumption. The self-sampling assumption says you should reason as if you are a random sample from the set of all observers in your reference class. The self-indication assumption says that the mere fact of your existence is evidence for hypotheses under which many observers exist. These two assumptions lead to different and sometimes conflicting conclusions about the simulation probability. Which one to use is not settled. The philosopher David Deutsch has argued that the anthropic principle is never a legitimate scientific explanation because it explains nothing causally. The debate is technical, philosophical, and unresolved. It matters enormously for the simulation hypothesis because the hypothesis's main probabilistic argument depends on getting the anthropic reasoning right, and there is no consensus on how to do so. The title of this script promises to examine a theory that scientists don't want to talk about, and it is worth being precise about what that means and what it doesn't mean. Most working physicists don't want to talk about the simulation hypothesis for a simple reason. It is not productive for their careers. The hypothesis in its most general form makes no testable predictions and therefore generates no publishable experimental physics. Time spent thinking about it is time not spent on problems that can actually be solved and published and funded. There is also a social dimension in a field where precision and rigor are the primary virtues. Association with a hypothesis that is widely perceived as speculative or even fringe carries a professional cost. Physicists who publicly engage with the simulation hypothesis risk being seen as more interested in science fiction than in science. This is an unfair association given that the hypothesis connects to genuinely fundamental questions in physics. But social perception is not always fair, and professional caution is rational. But there is a third and deeper source of discomfort, one that is rarely named explicitly. The simulation hypothesis, if true, would dissolve the foundational assumption of physics as it has been practiced for 4 centuries, that it is studying the universe as it actually is, discovering laws that are not contingent on any external agency, finding a reality that simply is the way it is because of nothing but itself. The laws of physics are not rules someone decided on. They are the way things are, and finding them is the deepest form of knowledge available to any mind. The simulation hypothesis threatens this entire picture. If the universe is computational, the laws of physics are the rules of the simulation chosen by whoever or whatever is running it. The constants of nature are parameters in a program. Physics, instead of discovering the fundamental structure of reality, would be reverse engineering someone else's code. An important enterprise, perhaps, but a fundamentally different one. Among the physicists who have been willing to sit with the discomfort publicly are some significant figures. Max Tegmark at MIT has developed the mathematical universe framework that partly dissolves the question. Neil deGrasse Tyson, in a widely circulated 2016 panel discussion, estimated the probability of the simulation hypothesis at 50-50 or better, based primarily on the acceleration of computing technology. James Gates Jr., a distinguished string theorist at Brown University, who has served on multiple U.S. science advisory boards, has written about finding error-correcting code structures, specifically mathematical objects called adinkras, embedded in the mathematics of supersymmetry, and has suggested cautiously that this deserves attention as a possible signature of computational structure in fundamental physics. None of these figures claim certainty. All of them are engaging with the question seriously, which is more than most of their colleagues are willing to do publicly. There is a version of this question that goes deeper than the simulation hypothesis in its standard Bostrom formulation, and it comes from taking seriously what modern physics has already established about the relationship between reality and mathematics. The physicist Max Tegmark at MIT has developed this into a full philosophical position, which he calls the mathematical universe hypothesis, and which he laid out in his 2014 book, Our Mathematical Universe: My Quest for the Ultimate Nature of Reality. Tegmark's starting point is an observation that is easy to state, but very difficult to absorb. Modern physics does not merely describe the universe with mathematics. The entities physics identifies as fundamental are mathematical objects, not physical things that happen to be described by mathematical equations. Mathematical structures that are identified in the equations with physical reality itself. An electron's quantum state just is a vector in a Hilbert space. The electromagnetic field just is a particular kind of fiber bundle equipped with a connection. Spacetime just is a pseudo-Riemannian manifold with a metric. There is no electron underneath the mathematics, no physical substrate that the mathematics is approximating or pointing at. The mathematics is all there is as far as any experiment has ever been able to determine. If you ask what the electron really is beyond its mathematical description, physicists either look at you blankly or tell you with some philosophical embarrassment that the question may not have a meaningful answer. If this is right, Tegmark argues, then the distinction between mathematical structures that exist in some abstract sense and mathematical structures that we happen to inhabit is not a meaningful distinction. All self-consistent mathematical structures exist in the same sense that ours does. There is nothing that makes our particular mathematical structure more real than any other. We happen to be observers within this one because this one produces observers capable of finding themselves in it. The structure of our universe is a specific mathematical object, the standard model of particle physics coupled to general relativity plus whatever completes quantum gravity. And it exists as a mathematical object in exactly the way that any other mathematical object exists. It is as real as any other, no more, no less. The connection to the simulation hypothesis is that if reality is fundamentally mathematical, then the distinction between being computed and really existing begins to dissolve in a specific way. A mathematical structure that is computed and a mathematical structure that exists are in Tegmark's framework the same thing. There is no substrate of real physical reality underneath the mathematics that distinguishes the genuine article from a computation. If you could perfectly compute our universe's mathematical structure, you would not be simulating reality from outside. You would be instantiating reality from the same level. The simulation question in this framework does not have a sharp answer because the distinction between simulated and real dissolves into the question of which mathematical structures exist, and by Tegmark's lights, they all do. This is a minority position among physicists, and it has been criticized from multiple directions. The philosopher Tim Maudlin has argued that Tegmark conflates two very different senses of exist. The mathematical sense in which a consistent structure is well defined, and the physical sense in which something is actually present in the world. David Deutsch has argued that the mathematical universe hypothesis cannot explain why the universe has the specific computational structure it does, since it claims all mathematical structures are equally real. But the universe we inhabit has a very particular and surprisingly structured character. And some philosophers argue that mathematics as a discipline is a human construction, not an autonomous realm of objects with independent existence, which would make the hypothesis circular. Whatever its ultimate validity, the mathematical universe hypothesis clarifies something important. The simulation question may be not just unanswered, but unanswerable in any empirical sense, because the answer depends on a distinction between really existing and being computed that may not correspond to anything physically testable. If the universe is a mathematical structure and mathematical structures just exist, then asking whether this mathematical structure is really existing or merely being computed is like asking whether the number 7 is really 7 or just a computation of 7. The question may be genuinely malformed, and this is not a comfortable resting place because it means the most fundamental question about the nature of the universe may be permanently beyond the reach of any observation or experiment. Not because we lack the tools, but because the question itself may presuppose a distinction that nature does not make. In 2015, three physicists named Ahmed Almhiri, Shi Dong, and Daniel Harlow published a paper that drew a precise and unexpected analogy between the holographic dictionary of ADS-CFT and a well-developed branch of computer science, quantum error correction. The paper, Bulk Locality and Quantum Error Correction in ADS-CFT, appeared in the Journal of High Energy Physics, and it has become one of the more cited papers in theoretical physics in the decades since. Quantum error correction is the science of protecting quantum information from the inevitable noise and decoherence that threatens any physical implementation of quantum computation. The central idea is that you do not store quantum information in a single qubit, which might be disrupted by a single error. Instead, you spread the information redundantly across many qubits in a pattern that allows you to detect and correct errors by measuring the whole rather than any individual part. The patterns used for this, called quantum error correcting codes, have specific mathematical properties that relate the information stored, called the logical qubits, to the physical qubits that carry it. One of the key properties is that you can recover the logical information even if some of the physical qubits are lost or corrupted, as long as you haven't lost too many. Almhiri, Dong, and Harlow found that the way spacetime information is encoded in the boundary theory in ADS-CFT has exactly the structure of a quantum error correcting code. The information about what happens in the interior of the spacetime is encoded on the boundary in a redundant distributed way. You can recover the full interior physics from any sufficiently large piece of the boundary, and losing small pieces of the boundary does not destroy the interior information. This is not a vague analogy. It is a precise mathematical correspondence checkable in detail. Think about what this implies. Error-correcting codes are designed objects. They are the product of deliberate engineering chosen to protect information against specific types of noise. The Hamming code, the Reed-Solomon code, the surface code used in quantum computing all exist because someone designed them to solve a specific problem. The fact that the relationship between bulk spacetime and boundary quantum theory has the specific structure of a quantum error correcting code was not put in by hand. It emerges from the physics of quantum gravity. Nobody designed it, but it looks like someone designed it. Patrick Hayden at Stanford University and John Preskill at Caltech had shown in a 2007 paper, now called the Hayden-Preskill paper, that information thrown into an old black hole, one that has already radiated away more than half its entropy in Hawking radiation, is returned almost immediately in highly scrambled form in the subsequent Hawking radiation. Black holes are extraordinarily efficient information scramblers, and the structure of that scrambling is related to the error-correcting structure of holography. The universe seems to be very good at not losing information in a way that looks to the eyes of a computer scientist like it was engineered to be that way. Whether this is evidence of design or simply a deep mathematical truth about how gravity and quantum mechanics must coexist, if they are to coexist at all, is a question that has no agreed answer. But the structure itself is real, and it is strange enough to deserve attention. If the universe is a simulation, the physics of the simulation, the laws that govern the motion of particles and the structure of spacetime within it, are the laws that any inside observer would discover by doing physics. There is no additional feature of physical reality that would be detectable from the inside and that would signal simulation. The simulation would be, by design or by the nature of what a successful simulation must be, indistinguishable from the inside from a real universe. Any observation that can be made inside is equally consistent with being inside a simulation as not being inside one. This is not merely a practical limitation waiting to be overcome with better instruments. It is a structural feature of the question. The only avenue that does not face this limitation is the one explored by Bean, Davoodi, and Savage, looking for artifacts of the simulation's architecture. Features that arise not from the intended physics of the simulation, but from the specific computational substrate it runs on. A cubic lattice imposes a preferred set of directions that the intended physics would not have. This is a crack in the design, a place where the implementation leaks through the surface of the physics. And it is the right place to look because it is the only place where the simulation's contingent architecture, as opposed to its intended physics, would be visible. But any simulator sophisticated enough to create a universe that has remained physically consistent for 13.8 billion years would either not use a naive cubic lattice or would implement corrections that remove the lattice artifacts. The crack in the design, if it exists, is below our current resolution. James Gates Jr., the theoretical physicist at Brown University, whose work in supersymmetric field theory has included the observation that error-correcting codes called adinkras appear in the mathematics of superstring theory, has suggested that looking for digital signatures in the fundamental equations of physics might be a more promising avenue than looking in cosmic ray distributions. If the simulation uses specific information theoretic structures, those structures might appear as mathematical patterns in the fundamental laws independent of the specific physical substrate. This is a genuinely different approach with a different logical status from the cosmic ray search. The practical difficulty is distinguishing the mathematical structure that appears because the universe is computational from the mathematical structure that appears because it is mathematically natural for this kind of physics. And making that distinction requires knowing what the natural structures are, which we don't always know in advance. Wheeler's participatory universe, with its quantum probabilities that resolve into facts only when asked by a measuring device, is the physics equivalent of this structural puzzle. The universe seems to need an observer to be fully definite, but the observer is inside the universe, and the inside cannot see its own outside. We are inside something. We can map it with extraordinary precision. We can describe its laws with mathematics of astonishing power and elegance. Trace its history back to 1/100th of a second after its beginning and forward to 1,000,000,000,000 years hence. But we cannot step outside it to see whether the thing we are inside is made of what it claims to be made of, or whether it is made of something else entirely, something computational and contingent that was decided before any of us were here to ask the question. That is the situation. It has no resolution available, and it is in its way the most extraordinary fact about the most extraordinary thing any of us will ever be part of. There is a habit in discussions of deep, unresolved questions to close with either false certainty or false despair. Either. And so we see that the universe is indeed remarkable, and so we are left with nothing to hold on to. I want to try to do something harder, which is to close with honest uncertainty and with an account of why that uncertainty is, in the end, something other than a failure. The simulation hypothesis, taken at its most careful, is the observation that physics does not currently give us a way to rule out the possibility that the universe is computational. It is also the observation that several features of physics, quantization, the holographic principle, the fine-tuning of constants, the mathematical identity between reality and its description, are consistent with a computational universe in ways that are not obviously explained by any other framework. This is not proof. It is not even strong evidence in the statistical sense. It is a set of features that happen to fit a picture. And fitting a picture is not the same as confirming it. What makes the question worth taking seriously is not that it has a likely answer. It is that it is asking something real. At the deepest level accessible to current physics, the universe looks like information. Not like information in a poetic sense, but in a technical sense that has precise mathematical expression, in the Bekenstein entropy formula, in the Maldacena correspondence, in the Almhiri-Dong-Harlow error-correcting code structure. Whether that information is real in a non-computational sense, whether there's a bedrock of physical stuff underneath it, is a question that current physics genuinely cannot answer. Wheeler spent decades asking this question and never found a satisfying answer. He did not regard this as defeat. He regarded it as the appropriate condition for a mind honestly confronting the frontier of what is known. The universe, he said late in his life, is a participatory universe. Reality is not independent of observation in the way classical physics assumed, and the nature of the relationship between observation and what is observed remains genuinely mysterious. The simulation hypothesis is the most recent version of the oldest question. What is real, and how do we know? It is dressed in the language of computing because we live in an age when computing is the most powerful technology we know, and our analogies for the universe necessarily reflect the most powerful tools of the time. Newton's contemporaries sometimes thought of the universe as a clockwork. The 19th century thought of it as a thermodynamic engine. We think of it increasingly as a quantum computation. These analogies are not necessarily wrong, but they are also shaped by what we know, and what we know is always partial. If there is one thing that the long history of physics teaches, it is that the universe is consistently stranger than our models of it. Newtonian mechanics gave way to relativity, which gave way to quantum mechanics, which gave way to quantum field theory, which is currently giving way to something we do not yet have a name for, some synthesis of quantum mechanics and general relativity that will undoubtedly be as surprising as its predecessors. The simulation hypothesis may be the framework that replaces our current one, or it may be a stepping stone towards something none of us has yet imagined. Or it may be, in the end, a false trail. What it is not is a question that can be dismissed by anyone who has looked at the evidence carefully. The universe is made of something strange at its deepest level, and that strangeness fits computational descriptions with an uncomfortableness that serious people have been unable to stop noticing. Whether the uncomfortableness is the discomfort of a truth trying to get through, or the discomfort of an idea that doesn't quite fit but rhymes tantalizingly with what we see, is the question at the frontier. The most terrifying thing about this theory is not that the universe might be a simulation,